It's my pleasure to introduce our keynote speaker, Dr. Brian Spears, who is Director of our Artificial Intelligence efforts at Lawrence Livermore National Labs. Brian got his PhD from Berkeley. In his research, he applies cognitive simulation techniques to stockpile stewardship missions with an emphasis on quantifying uncertainty in inertial confinement fusion experiments and developing a new generation of self-driving laboratory systems. In his current role, he is responsible for setting the vision for development and deployment of AI methods for national security missions. He is also the lead for the Livermore AI Innovation Incubator, which develops public-private partnerships and collaborative research projects to advance scientific AI in the national interest. He is the recipient of 2 Secretary of Energy Achievement Awards, multiple National Nuclear Security Administration Defense Programs Awards of Excellence, the Hyperion HPC Innovation Award, and the HPC Wire Editor's Choice Award for Best Use of High-Performance Computing and Energy. Please join me in welcoming Dr. Brian Spears.
All right. Thanks everybody and thank you for the kind introduction. It's a privilege to be here with you today, and it's especially a privilege to have followed such a nice setup by Siva, Venki, and Earl. I hope that I can entertain you today. I will not be as funny as Earl Lawrence, so I wish I would be, but I'm not going to. I want to, we had some detailed technical talk and some high-level vision. I'm going to zoom out even one more level to what we're doing for the nation-scale efforts in AI for science and engineering, and that will be encapsulated in what we're doing in our Genesis mission through DOE. My background, as you heard, is there's really 2 pieces of the way that I come to this conversation. One is with my AI hat on for helping drive the Genesis mission, but the other is having led the modeling and simulation half of our inertial confinement fusion program at Livermore on our quest to achieve fusion ignition in the laboratory for the first time. So, you can sort of filter that. You could read that as I failed for 18 years in my job until we finally succeeded, so don't expect something very quickly. Or we're putting everything that we know how to do for missions of national priority into meeting a very urgent moment. So hopefully you'll see it as the latter. But with that perspective, I've spent the largest part of my career harnessing predictive science tools and trying to accelerate them with new data science, machine learning, AI capabilities, just so that we could do essentially one thing, which is make a prediction and observe the discrepancy with reality and close that loop as quickly as humanly or computationally possible. So it's sort of from that frame that I would like to approach the conversation today. I'm going to talk a lot about Genesis and AI, but in the background will be what's in your heads and what's in mine. How do we use predictive tools at scale to understand the world and to figure out what it is that we don't know, and then go eliminate those knowledge discrepancies and go do something completely novel for the first time in human history. So with that, the background for the AI piece comes from disruption. AI is disrupting scientific discovery and national security science, full stop. It's not something that's coming or something that might happen. It is absolutely here and occurring. It's happening on the global stage. We are working as hard as possible in the United States, and our global adversary, principally China, has said that they will dominate us in this field by 2030. And when they've made claims like that in the past, they have followed through. So there is a sense of urgency with which we attack this. The AI tools that are changing how science is done are here. They're happening at scale. We can see it in coding. We can see it in the work that Siva and Earl were showing us. We can see it in the connection to model-based systems engineering that Venki has talked about, and I'll make some connections to that later. The Genesis mission is going to uplift US AI, both public and private, for those efforts. And then what I would say after that is that's going to bring a new way to close predictive science loops that we've not seen before. So there were glimpses of that in what you've heard earlier, but I'll try to foot stomp the way that I think we will move in the future. So the offer for us today to think about is issuing in a new paradigm for advancing predictive science. So let's dig in just a little bit more. I think it's been clear from the other talks already that what is happening in the world is, yes, there have been new AI reasoning capabilities, and it's always been fun to use a chatbot to write a tone poem in the style of a Southern Baptist minister or whatever. That was cute and that was nice 2 years ago. But what we can do now is use those to harness and steer our most powerful scientific capabilities. And it's at the connection between everything that we have known how to do before AI with these new AI capabilities that the frontier exists. So it is to use AI to help us discover new materials. But if we discover a new material, we don't just drop it into our complex engineering systems. We need agents that can help us redesign those systems to take account of those new materials that we have produced. And as we've learned in the National Nuclear Security Administration, it's not good enough to make a perfectly performant system that is infinitely costly to produce. We need AI-driven tools and capabilities that are aware of our design for manufacturing so that we can build not just the device that works, but the device that we can actually make on timescales that we need to deliver. And finally, we deploy these systems that are high consequence. Literally, global security relies on the devices that we build in lots of applications, whether it's AFRL or NNSA or DOE or other places. We have to make sure that they don't turn to goop 3 months after we make them, which means we might put a recursive pressure back on design me a material so that A and B can sit nicely next to each other if it's flooded with radiation or whatever happens. So that loop has to close. We've been doing fairly well as a scientific community about working in those silos. We have not had the cross-silo integration, the full mission integration to go out and attack these things in closed form with national scale and the pace that the global moment demands. And so really that's what's on offer for us from the Genesis mission. So think integrated capability, rapid delivery on problems of national importance. So the Genesis mission is exactly built to meet that moment. It's a national effort to accelerate science and national security. And I will phrase it as there are two major goals that we're aiming at. On the open science side, it's to double the impact of R&D from the nation. So currently the country spends about 3.5% of its GDP on R&D, which pays dividends in technological advancement for both security and for economic competition. We want to make that feel like 7%. 7% GDP and R&D would be far and away the biggest investment on the planet and in all of human history. So we can do that without effectively sapping the GDP to go do that. On the other side, with my national security hat on, I think of this in terms of innovation overmatch. We need to be able to mint new solutions and mitigate threats on ridiculously short timescales so that we can outrun our adversaries in every direction in which they wish to compete with us. And Venki mentioned some of this for putting tools in the hands of warfighters. This is exactly what we're thinking about. Putting tools in the hands of the nation for techno-economic competition, curing diseases when we're in a fight with the pathogen that Earl caused when he was here in 2020, or other things that are difficulties. So those two things, innovation overmatch and competitive dominance, are the goals. This is a mission-first capability. So it's super awesome to do AI, and I love to nerd out on it, and it's great, but it only matters if we transform what the nation needs. So we're attacking these in three principal lanes. The first is national security, where we were thinking about nuclear security and our intelligence missions. The second is science discovery, where we're trying to understand the way molecules actually work, go from quarks to cosmos on those scales of human and universal existence. And then also energy dominance, where we're thinking about fusion power that you can plug into, not just the thing that happens in a research lab like I spent my career working on, advanced nuclear, intelligent grids, et cetera. So there are, inside the Genesis mission, 27 clearly articulated challenges that we're going to go after, roughly split 9 in each of those 3 lanes. And those are our focus. We call them often lighthouses. Those are the things that if you are in a stormy sea in the dark, you can look to the shore and try to find which directions it is that you need to go. So we need to solve those problems, but we also need those problems to put evolutionary pressure on our tool sets and our capabilities so that we know what to build, so that we know that we are generating tools that are not hammers in search of nails, but are the actual tools that are going to deliver on the missions that we have to have. So to do that, here's the how. It's what we call the Genesis platform. It's going to bring those accelerated solutions to mission problems. It's going to offer that integrating center so that we are not all independently inventing wheels that we all wish we had, but that we didn't really want to produce. We just wanted the capability so we could attack our mission problem. The platform fundamentally looks like this. I mean, this is like the world's highest level architecture diagram for what we're working on. On the left, you have strong reasoning AI capabilities. We will build on the shoulders of OpenAI and Anthropic and Google. But we will take those AI capabilities and we will put them in control of the 8 decades of build out from the Department of Energy since the Manhattan Project. In 3 principal ways: it's high performance computing, it's high precision experimentation, and high consequence production. Those 3 things coupled by AI into self-reinforcing and self-improving loops. That is the vision that we put on the table, and then we ask ourselves, how do we build it? We build it with computational capabilities already delivered by pieces, some of which you've heard about, by Banyan from Siva and Sandia, by Artemis from Earl and Nathan and others here in the room, and we also innovate on top of that at scale and at pace. So the platform is how we will attack our national challenges. In our discussion today, what I hope you'll be seeing is a completely new way to close the predictive loop. Now, a closed loop is not a new idea at all. A fast closed loop with computationally driven reasoning and effort is a new thing to do. So I come from inertial confinement fusion, where we have an idea. It takes us a lead time of about 6 months to build out the target. We field that in an experiment that costs $1 million. We spend about 6 months thinking about what we just did, and then we have another idea to go on. So there's like a year in that cycle to have an observation, a prediction, a hypothesis, a prediction, an observation, and keep that loop closed. So there's nothing magical about what I think we're going to do with AI. Actually, I do think there is. But at the very first level, there's nothing magical. We're just going to take that loop and automate it and shrink all the timescales that are computationally reducible and make them far, far shorter. And that includes some of the computational and predictive pieces. I think Earl set it up nicely. With fine-tuning, there's a way to take out 75% of the cost and make effectively our supercomputers 4 times bigger than what they were before. That's what we need to do while reaching to the edge, closing the loop, and bringing in experimental validation data back into those predictions. So Venki mentioned that experiments are something like the ground truth, which, having struggled with experiments for my whole career, they're lies. Like, it's not true. They have error bars. You don't always know what you're observing. There are things you're missing. So nothing personal, Venki. Just, I have a thing with experiments, being the mod sim guy. But we have to put both of them. Yeah, I know, preaching to the choir. But we do need the ground truth to confront those predictive capabilities and understand what matters in the prediction, what doesn't matter in the prediction, where are our knowledge gaps, what are we getting wrong, and I'll try to highlight some of this in the more technical pieces. But the first thing that we just need to show is, what does a platform actually look like? So we're trying to work at startup pace inside a national bureaucracy, and this is some work that Earl and Siva and Nathan and others delivered in the first couple of months that we were working. We have really new, hot off the press stuff that is just not quite ready for prime time yet. Here's what you should feel for the platform. We're going to show you elements of the things that you've already heard about today operating as one capability. This is going to be the development of a multi-physics system, a shaped charge, an explosive system that you can use to poke holes in things or close high-pressure valves, things like that. We're going to ask for a hypothesis. We're going to see that get meshed up, executed, analyzed, and then an answer returned to us as the designer, doing all the things that I never wanted to do in my career. I never wanted to untangle a mesh. I never wanted to have to go slave over an EOS table to make sure that it was the right thing. I never wanted to restart my simulation on Saturday morning because it crashed at 5:01 p.m. on Friday when I left, and which happens every single time. So we have agents to do this for us now. Here you see us query a database from Pacific Northwest National Laboratory. Hey, tell us what we know inside DOE about shape charges. It comes up with some ideas. Look, the opening angle of the liner matters, the material that it's made out of, where the detonator is. These are all the things that are important about shape charges. If you're thinking about it, you should hypothesize in this space. Then it goes off, grabs a tool from Los Alamos and says, given that idea, look over the internet and everything that's known about science and figure out a hypothesis for something we could do that might be better than what our knowledge is right now. So it goes through and says, hey, look, I care about penetration. I care about those things that the P&L agent had for me. Here's an idea. Now, given all of that, we prompt it to then go execute. It goes off to Sandia, grabs Qubit, meshes up the idea, takes that, looks for time on Tuolumne, the younger sibling of the world's largest supercomputer at Livermore, runs simulations in the Marble code, and then hands that off back to Los Alamos, where there is an agent that picks it up and says, I know a little bit about rad hydro codes and about multiphysics codes. I'm going to write some code to extract useful physics, and then I'm going to execute that code and hand something back to the user so that we can get a final answer. By the time that's done, there's an outcome that says, oh, the average density of the jet is X, and this is what we've done. At that point, what has happened is that we, as users, have asked the question, hey, look, search for what we know, and let's make something better. And then a bunch of mechanics that we wanted to go on, that I never personally wanted to do, happens so that we can now have an answer about the question that we had. Can we have a better shaped charge? What makes it better? There's now work for the human to do. So in Earl's pictures of what we want humans to do, we want humans to think, to suggest, to veto, etc. This is the process where the human takes an action. Veto it if it's a really dumb idea, or amplify it, suggest something different, add, recognize that there's a fault. There are still humans in this loop. We don't want to be bottlenecked by humans, but we don't want to be blind to what's going on by the agentic systems either. So under the hood are a bunch of details for us to go understand. What really matters is that there's some technologies here that are being integrated. Collections of agents that can do things, communicating through engineered context so we can pass ideas back and forth between those agents, harnessing very complicated computational resources, including hybrid cloud and on-prem capabilities, and circulating inside an infrastructure and framework that lets all of that happen by relatively painless prompting from a human. So that's underneath and making it happen. That is the very zeroth level thing that we'd like you to think about when you think about Genesis Platform. It's what we would like to think about as an emergent capability for the country so that all of you doing predictive science do not have to invent this. How many folks out there are working with agents? How many folks are building MCP connections to tools and to hardware and things? Yeah, a good smattering of you. How many of you really want to build MCP agents? How many really just want the damn thing to move in the laboratory or use the tool so that you can get your answer? Hopefully everybody that raised their hand. This is what we're trying to do. Bring these capabilities to groups like this so that there is tool for you to use, not a thing you have to build. And if you do a thing that you absolutely are the only person on the planet that you can do, we want you to be able to register it in a system like this and grow the capability for the country. So the first thing, the platform is really the first thing that can hold an entire mission in frame. So what do I mean? If you think about the national security missions that we do in an NSA or the deep science in DOE, we are very good about learning pieces of the problems in our silo. We have not had something that stripes that all together, where we can carry the idea from the beginning to the end. And part of our process drag is often in handing off those ideas. Our high performance computers are great for doing that at the computational math level, but they don't help us communicate very clearly with our design agencies that produce things. AI is the first technological promise of being able to have the idea and pass it off in a computational way where we can recruit computational effort to advance, refine, and build that solution as we go along without those stovepipes in between. So what does the platform offer then if we have that capability? We can go from science concept to execution in dramatically less time. We can test ideas in closed loops, like we're talking about here. We can automate simulation and exploration of complex design and science or predictive spaces. We can drive self-correcting 3D printers and hardware to take advantage of our constantly improving predictive capabilities. We can control light sources or entire facilities. So what I hope you're feeling is the escalation of scale. We're starting to think, how can AI drive my laptop? How can AI drive El Capitan? How can AI drive a 3D printer, the entire spallation neutron source, all of the facilities inside DOE? How do we unify and harness this? That's the mission that we're working on. And so what does the platform actually do? I think it's clear at this point. We're running self-reinforcing loops to compress discovery times, generate hypotheses in design, simulate, verify, and quantify uncertainty. No one is interested in black boxes that assert that an answer is right without us understanding, believing, and having ultimate faith in the answers that come out of it. Preparing and executing experiments in production. The less deterministic these systems are, the more we are going to rely on that source that is not actually a lie, ground truth, experimentation, to come back in, whether that's numerical experimentation to make sure we're actually solving the PDEs that we think we're solving, that we're getting solutions that satisfy rigorous bounds, that we're getting answers that are physically consistent, that match experimental data, et cetera. All of that has to be built into what we do in our predictive capabilities. And systems that learn by iterating and curating new data to identify where our knowledge gaps and fill them, not with a flood of data that will eventually cover the space where we have a hole, but to identify the most bespoke and highest value experiment that we have to go do to fill that gap, or the most bespoke set of simulations that we have to go do to fill out those gaps. So we're taking advantage of current AI technologies and delivering on these qualitatively new capabilities. And I think this room is fairly expert and in tune, but I still want to walk through what I see as the evolution of AI capabilities. Because as Venki said, agentic workflows 6 months in our hands at real scale with absolute transitions in the last 3 months, so February, March, April, things are happening. Let's just walk through. We have natural language and vision capabilities. We're building on top of those so we can capture hypotheses at a higher level. That's been moved on with chains of thought and strong reasoning capabilities. So it was very nice to see the O3 model that came out from OpenAI and follow-on models. That was a sea change for me. It was the first time that I got answers that I thought, oh, there's something that's useful in my science efforts that isn't laughably silly. But we've gone further. There are tool use capabilities. Those relatively good reasoners can now go out to the internet. They can steer your laptop. They can run your radiation hydrodynamics code. They can connect to printers and things in the real world. So now we have the data center. We have these models living in our computers, escaping to our data centers, escaping the data centers to the actual laboratory, and building our ambitions. That's great. But you can't have a human using these tools as a remote control. I do this with my kids all the time. If I have to ask you to clean your room and I have to come in and tell you that you have to pick up your shirt and you have to pick up your pants and you have to put away that thing, like you're actually costing me time because I could just do it instead of remotely controlling you. What we need is the next step. Yeah, sorry, my kids are gonna feel bad if I tell them that story, but it's true though. Agentic workflows for complex automation allow us to say, go accomplish a task without having to lay out the entire work plan to go get it done. It is programming, and I'll say this later, at a higher level of abstraction. We're not writing machine code. We're not writing compiled code or interpreted code. We're writing in a place that we don't have words for right now in sort of task space of we need to do this roughly, this roughly, this roughly. It feels, if we're doing it correctly now, like you're writing a project proposal. So for everybody who has done that, when you sit down and say, hey, there's a thing I think I can do in the world. And to do that, my back solution is I would do this thing, before that, this thing. Here's where we are, and this is the state of the art. I think these are the steps. That's the place that we can now operate with these agentic workflows. And finally, those things cannot go off and get confused when you launch them. That's where we were 6 months ago, and we are not there now. So the runtimes are days, the runtimes are weeks, where you can plan out those operations and ask them computationally to go execute to do really complicated things. And we can talk a little bit more about that. But those long contexts of lots of idea and for long runtimes over many days are a transformation in what's capable. And we, I think in this room, are the best position to take advantage of that. Because what the folks building these capabilities don't know is that there is an entire universe of very highly capable predictive codes and capabilities to tell us so much about the universe that these tools do not yet know. And all we have to do at this moment is put those together in these closed workflows, then go verify it with experiment, and we are doing things on timescales that humans have never been able to achieve before. So these are an entirely different way to go do work. If we just recast it for this audience, what we have in those blocks is the capability to write predictive tools. We can write code to accelerate the generation of our code bases. We can use our existing validated, verified tools to go explore predictive spaces at a pace, scale, and ambition that we've not had before. We can identify and plan key tests because we will discover shortcomings and we can go out to the edge and fix those with the most informative experiment. We can execute closed loop observation so that as soon as we've done that experiment, we can bring it back into the space and do what we've always known we have to do in the predictive sciences space, but at a pace that we can only imagine right now or could until today. And we can update the entire tool chain. We can answer what has to get better. Is it my experimental capability? Is it my target fabrication capability? Is it the simulation capability? Is it my ability to harness resources in a timely fashion? All of those things are on the table. And this is where we come back to, and I will steal exactly what Vinky said. I believe it firmly, and it's in my slides as well. Model-based systems engineering for the entire predictive tool chain is the thing that we have to go do. So in fact, for you, Vinky, I described this insight in an essay as, which do we do first? Digital transformation and model-based systems engineering, or AI transformation? And I describe it as inhalation and exhalation. If you would like to breathe, you should do them both. Otherwise, it's bad if you decide only to inhale and then to wait until you've done all your life's inhalation until you start doing the exhalation. Not a good strategy. Okay, this is just one note for this room because most of you are probably code folks. This is how I fundamentally think about what we've done in the moment that we're facing inside the AI world. We have already raised the abstraction level for the way that we do programming. If you look at especially the what I'll say is the easier world for code generation, at sort of commercial code and the way folks are building things for apps and services that are not as high consequence as some of the prediction that we do. Programming is operating in the way that you see on the left. Like, there's a question and a hypothesis that we might do. We might architect and build out a workflow. We might identify a computational approach, choose our code tools, maybe write interpreted code to do that, maybe write compiled code that's super highly performant that lives underneath that. And then there's stuff that are places where humans rarely look, where compilers do things for us and not many of us are paying attention to what's going on under the hood. Some of us are. I think Teresa will probably talk to you about the way that the implications for that in the world in the afternoon. But we used to have a single investigator working down at the compiled code level. We now have the capability to raise the sites all the way up to that, have a question and architect the approach, and then watch computational teams go off and do that. Now what we have to do for predictive science is not only turn that on our favorite tools, which are our codes, but also turn them on our experimental capabilities, our production approaches for making the targets and the pieces that we put inside those experimental facilities, and move us from the place of, I need to set up, and this is for Carolyn, I guess, I need to set up my experiment, I need to put a filter pack in place, I need to identify the cable that is going to give me the right timing for my experiment. None of us really ever wanted to do that on the experimental side either. We just wanted the camera to capture the flash that was going to come off the thing so we could answer, was this what we predicted and what we expected or not? So we're going to move the abstraction level above to the new level of, what is my question hypothesis, what's my workflow? That's what the Genesis platform is meant to do. And so hopefully you feel like it's a tool being built for you as a community. We've done this. We have systems that we care about where we're building out structural components. We have the platform now working on driving designs and making many hypotheses using topology optimization coupled with AI to say, here's what your structure could look like. We have put that platform, Siva has done this with the team, in control of actually printing physically the prototypes that we're looking at. A human, still in the loop, has selected the one that is a good idea and vetoed, in Earl's words, the ones that are a bad idea. We've gone on to the print of actual structural elements of enormous things that weigh thousands of pounds that are important to us. And we're doing integrated design for subcomponents and complicated systems that can live inside them with tools that Earl has talked about. All of that happening from start to finish. This is our scientific enterprise already functioning at some low level, just beginning to glimmer from the capabilities that we have in our platform. I want to show you this actually, not the platform, but the capabilities live for the first time that I was really excited about, an AI capability driving an experiment in really tightly closed loop. So this entire thing working for an ICF-like capability. So let me take you through an experiment that is AI-driven for the first time that I was really jazzed about. This is a super simple experiment. There is a plastic cylinder, and it's rotating, and there's a laser that's going to blow off a little explosion of plasma off the side of it. And it's going to fire once every second or so, or once every couple of seconds, and the little plastic cylinder is going to rotate. So the things that I can do is turn up the brightness of the laser and blow more stuff off of it, or there's background nitrogen pressure inside the target chamber, and I can turn up the pressure so that the explosive cloud that comes off gets squeezed more tightly or less tightly against the cylinder. And what I want to do is have an AI agent that's been trained on a surrogate model of a code and then an understanding of the experimental facility to take control of the brightness of the laser, and it's essentially the focal position of a lens. It's a little more complicated than that, but for now it'll do. I want it to be able to control the laser properties, and I want to say, sort of to Venki's point, we want to say what the mission is and then come back and say what capabilities we need. We want to say we want a blast cloud of a particular size, and then we want to engineer the facility in real time to deliver the blast cloud of that size. So here goes. What you'll see at the top right in X-ray vision is the cloud that's blowing off with the laser striking at the origin on the left. And we're going through asking for clouds of a different size. And the laser system is changing its controls, the AI agent doing that with humans hands-free. And you'll see that the bubble is oscillating a little bit in size, but it's vaguely close to the place that we're asking for. And we go in, and the next thing that we do at the very end is, and we as the royal we, it's a team of people that I'm quite happy to be associated with, go in and say, all right, now after asking for this thing, what you see at the bottom in the yellow is the nitrogen pressure. And so without telling the AI agent that we're going to change the nitrogen pressure, we say, hey, give us a fixed bubble size, and then we go in and we lie to it. and we change the background pressure, and it has to fight with what it knows about physics in order to figure out how to adjust the properties of the laser system in order to keep the bubble that's blown off at about the size that we asked for. So that's super exciting. This is hello world of the closed loop that we can identify. There is a predictive code in all of its glory as the foundation of all of this running on HPC. There's a surrogate model on top of it. There's an AI agent that understands that and the control of this system. And then there's real-time closed loop to accomplish something. There are also errors because experiments lie to you sometimes. It turns out that if you look at the bubble oscillating, there's a periodic oscillation. Why is there a periodic oscillation when we're firing on a new piece of the target every time? Turns out it's because the rotating target was slightly bent. So every once in a while in the rotation, it was a little bit closer to our laser, and focal distance is what we were changing. And every once in a while, it's a little farther away. So the experiment is a bit of a lie, because what we told the simulation world was happening was you were firing a perfectly coaxial thing that's spinning about its axis, and that's not actually what was going on. We saw it in the data. Humans realized it about 30 minutes after our very high-cost 45-minute execution window. We believe now that after catching that, had we had some Claude agents that we're building, working with Anthropic, running, that we would have recognized by computational agent what was going on, and we would have taken out that wobble by control to figure it out in real time running the experiment. The next experiment we go do, what are we going to do? We're going to put that thing in there, we're going to actually bend it, and then we're going to try to put a Claude agent in control to help us feed back and take out from what we know about without knowing the experimental conditions, but what we know about physics from our predictions, can we make that a cleaner experiment and make it better? So those are a couple of glimpses of what we're doing inside our capability. We have rapidly advancing US AI. We have the Genesis platform that's harnessing what we're doing on the private side from OpenAI, Google, Anthropic. We have the prediction ecosystem that is being built by academics, by the national labs, by this group, and we're putting those in closed loop. I'll just end by saying, as amazing as this stuff is, we cannot possibly do this alone. This is a whole of nation effort. We have more than 30 members in our Genesis consortium. These are the OpenAIs, the Anthropics, the Googles, Microsofts, AMDs, NVIDIAs, coming in to build out these capabilities with us because they recognize two things. One, that it's a moment that the US has to win, and so they are in. And two, that the DOE, and I'll say predictive sciences community, has unique capability that they need to be adjacent to in order to know what they know and what they don't know, and to make advanced progress on the world's most complicated reasoning problems, some of which come from our predictive sciences community. So let me end by saying what I said before. The Genesis mission is harnessing AI to transform science for the country. You can see that I give IFE talks. IFE should be a key success. That's inertial fusion energy. So 18 years of inertial fusion, and I can't quite get it out of my talks. But there are a couple pieces. There's the Genesis platform. That is our technology push, the capabilities we have to generate. Those will be driven by our Genesis science and technology challenges, the 27 key vectors that we have to attack inside the country. And there is a rapidly changing US AI ecosystem that we are, each of us, trying to struggle to keep up with. Genesis is meant to give us the capability to harness that and to keep a pace a little more nimbly. And then I'll end with my thesis and challenge for this community, that it offers us a new paradigm for advancing predictive science. And I hope that we might all work together to make sure that that is not just a dream, but actually a reality. Thanks.
All right, so we'll start with some questions from Pigeonhole. The first question, you mentioned the gap between the builders of foundational reasoning tools and the DOE's deep physics codes. Practically, how is Genesis handling that translation layer? Are you building rigid APIs for codes like Marble, et cetera? Or are models like O3 being trusted to dynamically write their own execution or even meshing scripts?
Yes to the first, no to the second. And so let's reframe that a little bit. We are absolutely writing APIs to code so that we can use those tools and take those capabilities and make them be worth everything that they are. We want to exploit those. We are not imagining right now reasoning models refactoring and writing those predictive capabilities on the fly. Let me say one reason why. If you want to predict an experiment at the National Ignition Facility, you can grab a 1D, a 2D, a 3D radiation hydrodynamics code that is super great, that has passed every regression test on the planet, and you'll still get the wrong answer of what's going to happen in the experiment. because there are things we don't know, because there are settings and choices that you have to make that take a tremendous amount of expertise to reflect data that we've seen, to account for the things that we don't know. Asking a reasoning tool right now to do that would be folly. Maybe in the future, but certainly not right now. There are whole rabbit hole we can go down. But there is something that we are working on right now with the Frontier Laboratories, and that's building out a sort of Rosetta Stone or a translation layer between the output that comes out of codes and the things that reasoning tools can understand. So essentially, we've got spatiotemporally resolved fields that come out of all of our predictive capability. They're giant arrays of double precision numbers, and they mean effectively nothing to anything except humans right now. There's a shock wave flying through a target that's got multiple materials and multiple conditions. It's very hard for a reasoning tool to look at a tensor, a block of data that came out, and understand what's going on. But that doesn't have to be the case. So the intermediate to what we're suggesting is to put in closed reinforcement learning loops a high-performance computing code, making data that a model struggles to understand with closed-loop evaluations that we understand from the science community, so that we can train those things to recognize that there is a shockwave embedded in the solution that you see in the field, and that it can do the things that it needs to do. That's interesting to our partners. It's interesting to us. It's the way that we capitalize on our predictive codes and make sure that those codes can be maximally accelerated by the Frontier capabilities. So yes, take advantage of all the things that we're already doing. No, we are not going to reinvent that wheel by AI.
I'll use my prerogative as a session chair to maybe ask a follow-up, since you brought up expertise and the human. So my question is basically the human in the loop right now is, where do you see those bottlenecks, and where do you need the human? And then secondly, where do you see in the future, and you can choose how many years into the future or months, what do you see the role of the human to be?
Well, there's a thing we want to get rid of and a thing we want to keep. We want to get rid of the human as bottleneck. We want to keep the human as certifier, as steward. So those go back to the roles that Earl talked about. We can look at the development of agents for where the human could be as a function of time and where I think we're going to go. So we can sort of extrapolate. It used to be that for chatting, there was human has an idea, computational intelligence does a thing, returns, I process it as natural intelligence, and we go back and we iterate. It's a chat, right? That stopped being the case when we started having agents. When we had agents, agents could go off and do a thing, and you might build out an orchestration for those agents, and they go off and do things. So then the human is the limiting case at filling out what it is the agents should go do. We've moved to a place where there are teams of these things that can operate. So what the human has to do, teams of us, we have to build out those agents, give some orchestration capability to those things, and now we're bottlenecked at how many agents can we build and how can we orchestrate them. Now humans are that bottleneck. It looks like the frontier is remove humans from that bottleneck and put an orchestrating agent on top of it that has access to tool generation, to a file system, to build out the needed agents to create its team so it can go work. So what you see is the human moving up that continued ladder of abstraction to planning. Our job is twofold at every state, is to get the human out of the way of the bottleneck so the computational intelligence can work at its speed without sacrificing the fidelity of that operation, so that we can still have ideas, criticize, veto, understand what's going on. The careful listeners will probably find that falls a little flat at the end, because what we say is we're going to have humans do all the things they should do and none of the things they shouldn't. It's still not perfectly well defined, but we have some pattern over the last few months to understand.
Let me go back to the questions about the audience. Do you believe commercial foundation models and their content development, augmented with tools like RAG, are ultimately sufficient to grasp deep physical intuition? Or will we hit a ceiling that requires custom ground-up LLM training on bespoke DOE data?
I sort of hate to wade into this fray. That you can jump on Twitter and you can just listen to Gary Marcus and Jan LeCun on one side, and the $10 trillion or the $1 trillion on the other side. Look, my personal opinion is we're going to get really far with the architectures that are there right now. We ought to have a distributed portfolio where we bet on some other ideas as well. My take is we've gotten way farther with the current transformer-based architectures and some scaffolding around them than I ever thought we could have. So my opinion ought to count for about nothing in this. That said, it doesn't look like the scaling is going to stop. We have deep conversations with our Frontier Laboratory partners, and they are operating a good 12 months in advance of what they actually release and what we've seen, they're not seeing curves bending or turning over. They have a financial interest in making that statement, so that's not lost on me, but I, to this point, trust them. I do think world models and physics capability are inevitable in this. Whether it emerges from the sort of connectionist representations or we have to build that in, it's hard to say. I learned a lesson earlier in my career that I should never try to do with data science and machine learning what can be done by physics knowledge. There's just too much information captured in the 25 PDEs that we can solve to try to learn all of that with basic representations. That said, I would have said these current transformer models died a long time ago based on that. So you should take my opinion for valueless.
Let me jump a little bit because we have a number of questions and only limited time. Let me go to one question that was upvoted. Do you think there will be a global knowledge loss in new scientists who are using AI in this way?
It's a risk. We'll see. I don't think so. I'll answer from personal experience. In my ICF work, what I tried to do for decades was to do as many simulations as possible. Because my first experience with sitting down with a predictive code was to get a point estimate and not really feel in my scientist's heart whether that was a true answer or a robust answer or whether I was balanced on a head of a pin. So what I wanted to do was batch off hundreds of thousands of these simulations so I get a feel for the gradients and the stability of the solutions. And by doing that, some of the criticism that I got back from the physics design community was, well, you're not really looking at those simulations. You don't know what's going on. But in practice, what I believe happened to me and to folks who have worked in that way is that you had to understand at the larger level whether your solution was valid, whether your physicist and engineer's intuition made sense. Should that actually be a stable solution? Should it be sensitive to these perturbations? Do you have your codes set up in such a way that they can survive assaults by changes in resolution, changes in mesh strategy, changes in AIL, or whatever it is that you're doing? So you actually have to be a better physicist and engineer to understand as you move up the abstraction layer. So if we do this correctly, what we'll be doing is putting pressure on folks to use AI and get answers back that they have to think very deeply about as humans and be really good scientists and engineers. If we do it correctly, we'll train a bunch of hamsters that use it like black boxes, and we'll get back exactly the value of that hamster, which is not very much. So I'm pretty optimistic on the non-hamster outcome. But I will say for those of you raising the tools or using the tools, that it's a challenge. I use AI a lot. I write a lot of code, and I'm not a good programmer. I use it to solve problems. Like I went back and literally reworked my PhD dissertation in a weekend. Super cool, incredibly humbling. Wasn't as awesome as I thought, it turns out. But I have to be really good at looking at those solutions when it comes back and says, here's 10,000 lines of code, here's all the execution for these simulations, and here's a conclusion. Because I don't know whether that thing is reward hacking and it's telling me the thing that it wants to know without actually having done it. And so now I have to be in the position of asking the right questions. Is that real or is it not real? So you should put yourself in the position now of being an Oppenheimer or a Teller and say, what's it like to interact with those folks? Why were they good? Because a postdoc or a decade experienced engineer or physicist would come in and they would stare penetratingly into the problem and ask the one question that actually mattered, right? That's what made them an Oppenheimer or a Teller. Now we've all got to be able to go do that. So I think the pressure is for us to elevate our game and to work to go do that, not to be hamsters.
Great. I'm told that we can keep going for a little bit with questions. We'll make sure that you can go on in a timely fashion.
Yeah.
So next question is, looks like it is easier to eliminate friction in predictive science than in institutional and governmental structures to do big science at national scale. Your thoughts?
Yeah, I don't know what they're talking about. Like yeah, no, I mean, it is true, but there's a place where AI is a partial solution to even the friction problem. So I was careful in my statements, you probably heard it. I said we would take everything that's computationally reducible and we would reduce it. All the stuff that is not computationally reducible probably comes in two buckets. There are physics clocks that we just can't change. If you're culturing cells, they reproduce at the rate they reproduce unless you can turn up the temperature or whatever it is you can do, and you're limited in how fast they go. On the other side, there is bureaucracy, and there are rules, and there are decades of data that may not be digitized, that may be digitized at low resolution, and we have to figure out how to go do this. There's a slight bridge there where AI can help us read 10,000 documents of procedure, distill them into the 15 requirements that actually make sense, and then help us accelerate by working on that if we trust it. So the questioner is astute. It's true. There is a bunch of bureaucracy that is slowing us down, and politics and society are all difficult. But even that is tractable, because mostly what people are saying is, I have a job. It's my job to regulate what's going on. There's this really complicated process. What we do is high consequence, and not on my watch are we going to screw up. And often that sense of not on my watch with no tolerance for risk is what slows us down. What we have to do is make the problem simple enough that people can recognize the risk that they're taking, see the whole problem, hold it all in frame, as I promised, and then make a decision where they can say, it's okay on my watch to get that done. We got to enable people. Nobody wants us to go slow, right? And AI might help us get better.
We have a question on, two questions related to working with Anthropic, OpenAI, et cetera, that I'll combine here. So how much are you relying on customized domain-specific agents, so such as those developed by those AI giants, versus deploying off-the-shelf general-purpose agents? And then how has the supply chain risk label complicated these collaborations?
Yeah. So we're not doing much agent customization with them right now. We will in the future. So right now, the agents that we're using are either the off-the-shelf things that we can get our hands on, so things that look like Codex and Claude Code and other derivatives of those, or we are using our own in-house capabilities and agents, the one that Earl has talked about. We have inside the Genesis platform over 300 DOE-produced models and agents that we can use for specific things like materials discovery and design. So right now, that's been our approach. What the frontier labs are interested in is that next step of, do they need agents built out that they can put through the sort of gauntlet of our requirements that can give them the capability that they can now use? And if we do that, do we get an answer faster than we could otherwise? And do they get a capability for the US that they wouldn't otherwise get? There's a value proposition in there that we are working on. Okay, so now the political question. The supply chain risk for Anthropic is a problem. About half of our cycles across the national lab, or the tokens that we use, come from Anthropic, the other half from OpenAI. Not exactly. There's an increasing share of Gemini and things coming from Google. Shutting that off turns off, it does 4 major things. It turns off our supply of tokens. It breaks particular agents' workflows, shuts off our research capability, and it takes down agents that are already based on top of Anthropic as their brain. And so we got to deal with all 4 of those things as we turn them back on. It's not clear exactly which way that's going to go. We're operating within what the administration says. It's paused right now, and so we're using Anthropic, but it's a challenge. There are really 3 major players in the US AI ecosystem: Google, Anthropic, and OpenAI, with maybe a distant 4th, an XAI. It hurts the US ecosystem to lose one of those players, and we just have to have trust across the government to get that done. I don't know what the way forward looks like.
We're almost at the end of the questions. One, hopefully a quick one about that's more related to hardware. If the goal is to put code outputs into AI tools that run at single or even half precision, is that where multi-physics codes need to compute?
Wait, is that where multi-physics codes need to compute?
Yes.
Oh no, I don't know. This is for the room. Ask Teresa when she comes up. I don't believe that reduced precision compute is probably what we want to do for the predictive physics. I think we just need to take representations on the reduced precision side and make them understand the structures inside the high precision side. Most of the features that we want to resolve in the precision codes are not themselves that high precision. It's the errors that accumulate over time that we have to guard against. So I think low precision representations of what's in the block of numbers is fine. High precision representations to keep that faithful is an entirely different story that we don't want to give up on, but I will leave that to the experts to talk about.
Great, and I'm sure we'll have more questions about that later. All right, let's end here. Thank you so much for.
Yeah, I have to apologize. I can't stay for the panel. So I'm trying to take the advice, because I have to leave, that was given to me by our administrator, which is be bright, be brief, and be gone. So you can debate about the bright, but at least brief and gone. So thank you guys.